Welcome! In this video, we'll tackle problem number 2058, find the minimum and maximum number of nodes between critical points. We'll explore efficient algorithms to solve this problem, breaking it down step by step. Let's dive in. In this problem, we are working with a singly linked list, where each node contains an integer value. Our goal is to identify critical points in the list. A critical point is defined as a node whose value is either strictly greater than the values of its immediate neighbors, making it a peak, or strictly less than the values of its immediate neighbors, making it a valley. Once we identify these critical points, we need to calculate two distances. The first is min distance, which is the smallest distance between any two critical points, and the second is max distance, which is the distance between the first and the last critical points in the list. If there are fewer than two critical points, we should return -1, -1 as the result. The input to the problem is the head of the singly linked list, and the task involves analyzing the values of the nodes in the list to determine the output. The output for this problem is a list containing two values, min distance and max distance. To clarify, min distance represents the smallest difference in indices between any two critical points, while max distance is the difference in indices between the first and last critical points in the list. If there are fewer than two critical points, the output should simply be -1, -1. For example, consider the linked list 3, 1, 2, 2, 3, 5, 1, 2. In this case, there are multiple critical points, and the output would be 1, 6. This means the minimum distance between any two critical points is 1, and the maximum distance between the first and last critical points is 6. In the linked list 3, 1, 2, 2, 3, 5, 1, 2, we can identify the critical points by analyzing each node and comparing its value to its neighbors. The first critical point is at index 1, where the value is 1, because it is less than its neighbors 3 and 2. This makes it a valley. The second critical point is at index 4, where the value is 3, as it is greater than its neighbors 2 and 5, making it a peak. The third critical point is at index 6, where the value is 1, since it is less than its neighbors 5 and 2, forming another valley. Now, if we calculate the distances between these critical points, the difference between indices 1 and 4 is 3, the difference between indices 4 and 6 is 2, and the difference between indices 1 and 6 is 5. From these, the minimum distance is 1, and the maximum distance, which is measured between the first and last critical points, is 6. Now let's consider another example with the linked list 1, 3, 2, 2, 1. Here, the first critical point is at index 1, where the value 3 forms a peak because it is greater than its neighbors 1 and 2. The second critical point is at index 4, where the value 1 forms a valley because it is less than its neighbors 2 and null. The distance between these two critical points is calculated as 4 to 1, which equals 3. Since there are only two critical points in this case, both the minimum and maximum distances are the same, and the result is 1, 3. In a third example, consider the linked list 1, 2, 3, 4, 5. Here, there are no critical points because the values in the list are strictly increasing. None of the nodes satisfy the conditions of being either a peak or a valley, since no node's value is strictly greater than or strictly less than its neighbors. As a result, the output for this case is -1, -1. When analyzing the constraints, we see that the number of nodes in the list can go up to 100,000, and each node's value ranges from 0 to 100,000. This means the solution must handle large input sizes efficiently without exceeding time or memory limits. To ensure a robust solution, we should consider several edge cases. First, if the linked list contains fewer than 3 nodes, it's impossible to have any critical points since there aren't enough neighbors for comparison. Second, in cases where adjacent nodes have the same value, they cannot form a critical point because the values are not strictly greater or lesser. Third, if the entire linked list is strictly increasing or decreasing, there will be no critical points, and the output should be -1, -1. Fourth, if there are exactly two critical points, the minimum and maximum distances will be the same, as there's only one possible distance to calculate. Finally, given the upper limit of 100,000 nodes, it's crucial to traverse the list efficiently, keeping track of critical points and calculating the required distances without additional overhead. To tackle this problem, one approach we can consider is the brute force method. The intuition here is straightforward. traverse the linked list and identify each critical point. A node qualifies as a critical point if its value is either strictly greater than its immediate neighbors, making it a local maximum, or strictly less than its neighbors, making it a local minimum. Once we've identified all the critical points, we store their positions in an array. Using this array, we can calculate the pairwise distances between consecutive critical points to find the minimum distance. Similarly, the maximum distance can be determined by simply calculating the distance between the first and the last critical points in the array. However, while this approach is simple to understand, it's not particularly efficient because calculating pairwise distances involves multiple traversals of the list. This makes the time complexity of the brute force approach O(n) squared, when there are many critical points, which can be quite costly for larger linked lists. Now, to improve upon the inefficiency of the brute force method, we can adopt an optimized approach that calculates both the minimum and maximum distances in a single traversal of the linked list. The key idea here is to maintain a few variables as we traverse: the position of the previous critical point, the position of the first critical point, and the position of the last critical point. Each time we encounter a critical point, we calculate the distance to the previous critical point and update the minimum distance if necessary. At the same time, we keep updating the position of the last critical point to the current critical point's position. Once the traversal is complete, the maximum distance is simply the difference between the positions of the first and last critical points. If the list has fewer than 2 critical points, we return -1, -1, since valid distances cannot be computed. This approach is much more efficient, reducing the time complexity to O(n), as we only traverse the list once. Additionally, an alternative approach could involve converting the linked list into an array of node values, which simplifies indexing and comparisons. However, this would require extra space proportional to the size of the list, making it less space efficient. The optimized approach, which involves a single traversal of the linked list, is the most efficient and balanced solution for this problem. By tracking the critical points' positions during the traversal, we eliminate the need for nested loops or additional data structures. One important observation here is that a node's critical status depends only on its immediate neighbors, meaning we don't need to revisit nodes multiple times. This allows us to perform distance calculations on the fly, avoiding any post-processing. The decision to choose this approach is driven by its efficiency, with a linear time complexity of O(n), and its minimal space usage, as it doesn't require storing node values in an array. Additionally, the logic is straightforward, which keeps the implementation simple. However, there is a trade-off: the optimized approach can be slightly more complex to implement compared to the brute force method. For scenarios where node values need to be revisited later, the alternative array-based approach might be more suitable. Still, the single traversal method offers the best balance between performance, space optimization, and simplicity, making it the ideal choice for solving this problem effectively. To tackle this problem, we need to identify critical points in a singly linked list and calculate the minimum and maximum distances between them. A critical point is a node that stands out compared to its neighbors. It's either a local maximum, where its value is strictly greater than the values of its adjacent nodes, or a local minimum, where its value is strictly smaller. The input is a singly linked list where each node has a value, and the output is 2 numbers, the smallest distance between any 2 critical points and the largest distance between them. If there are fewer than 2 critical points, we return -1, -1. To get started, we initialize a few key variables. The index variable will help us keep track of the position of each node as we traverse the list. We'll also use a list called critical_indices to store the positions of all critical points we find. To traverse the linked list, we'll use 3 pointers: previous, cur, and next, which represent the previous, current, and next nodes respectively. This setup allows us to efficiently determine whether each node is a critical point as we proceed through the list. Now we begin traversing the list. Since the first and last nodes cannot be critical points, we start at the second node, which has an index of 1. For each node, we check if it satisfies either of the 2 conditions for being a critical point. A node is a local maximum if its value is greater than both its previous and next nodes, and a local minimum if its value is smaller than both its previous and next nodes. If the current node meets either of these criteria, we add its index to critical_indices. The traversal stops at the second to last node, since the last node, like the first, cannot be a critical point. Once we've identified all critical points, we calculate the distances between them. If there are fewer than 2 critical points in the critical_indices list, we return -1, -1, as it's not possible to calculate meaningful distances. Otherwise, we calculate the minimum distance by iterating through the list of indices and finding the smallest difference between consecutive elements. For the maximum distance, we simply use the difference between the first and last indices in the list, as this will always be the largest possible gap. At this stage, we return the results as a list containing the minimum and maximum distances. Let's reflect on some key insights from this approach. First, the definition of critical points ensures that we focus only on nodes representing significant changes in the values of the list. This makes our solution both precise and efficient. Second, storing the indices of critical points in a list allows us to calculate distances in k time, where k is the number of critical points, a significant benefit in terms of performance. Finally, we account for edge cases such as having fewer than 2 critical points, which leads to a default output of -1, -1. Similarly, if all values in the list are the same, no critical points will exist. Additionally, we recognize that the first and last nodes cannot qualify as critical points, so they are naturally excluded from our calculations. The algorithm relies on 2 key data structures, the singly linked list, which serves as the input, and a list, critical_indices, which stores the positions of critical points. The singly linked list ensures that we process nodes sequentially, maintaining the order of traversal. Meanwhile, the critical_indices list provides constant time access to the indices, enabling efficient calculations of both minimum and maximum distances. Regarding complexity, the time complexity of the algorithm is O(n), where n is the number of nodes in the linked list. This is because we traverse the list only once, examining each node a single time. The space complexity is O(k), where k is the number of critical points, as we only store their indices. This efficient use of both time and space makes the algorithm well-suited for large inputs. Let's walk through an example to see the algorithm in action. Suppose the input is a linked list with the values 1, 3, 2, 4, 1. As we traverse the list, we identify the critical points. The node at index 1, with a value of 3, is a local maximum because it is greater than both its neighbors, 1 and 2. Similarly, the node at index 3, with a value of 4, is a local maximum because it is greater than both its neighbors, 2 and 1. We append these indices, 1, 3, to the critical_indices list. Next, we calculate the distances. The minimum distance between the critical points is the difference between consecutive indices, which is 3, 1 equals 2. The maximum distance is also 3, 1 equals 2, as there are only 2 critical points. Therefore, the output for this example is 2, 2. Here, we start by defining a method called nodes between critical points within our solution class. The goal is to calculate the minimum and maximum distances between critical points in a linked list. To do this, we initialize several variables. First_CP will hold the index of the first critical point, while prev_CP will track the index of the last encountered critical point. For the distances, we set min_dist to infinity as a placeholder for the smallest distance, and max_dist is initialized to -1 since we haven't calculated any distances yet. Next, we set up pointers, previous for the previous node, cur for the current node, and cur_index to keep track of the position in the linked list. As we traverse the list, we check if the current node is a critical point. A node qualifies as a critical point if its value is either a local maximum greater than both its neighbors or a local minimum smaller than both its neighbors. If we find a critical point and it's the first one, we update first_CP to hold its index. For subsequent critical points, we calculate the distance from the last critical point using cur_index, prev_CP, updating min_dist accordingly. Additionally, the maximum distance, max_dist, is updated as the distance from the first critical point to the current one. Once the distance calculations are updated, we also set prev_CP to the current index to keep track of the latest critical point. After processing the current node, we move to the next node by updating previous to the current node, advancing cur to the next node in the list, and incrementing cur_index. The traversal continues until there are no more nodes or neighbors to check. After the loop, we handle the edge case where fewer than 2 critical points were found. In such scenarios, since we cannot calculate any meaningful distances, we return a result of -1, -1. If there are at least 2 critical points, we return the calculated min_dist and max_dist as a list. This ensures that our solution handles all edge cases and provides the correct output for valid inputs. Here, we start by defining the method nodes between critical points, which takes the head of a singly linked list as its input. We initialize several variables to help us keep track of critical points and calculate the desired distances. Specifically, first critical point and prev critical point are initialized to -1, which will later store the positions of the first and previous critical points, respectively. We also define min distance to track the smallest distance between any 2 critical points and set it to integer.max_value as a starting value. Similarly, max distance is initialized to -1 to store the maximum distance. Next, we set up pointers, previous to track the previous node, cur for the current node, and index to keep track of the position as we traverse the list. The while loop then begins, and it ensures that we stop when we reach the end of the list or when there are no more nodes to compare. Inside this loop, we check whether the current node is a critical point. A node qualifies as critical if it is either a local maximum or a local minimum compared to its adjacent nodes. This check is implemented using the condition cur.val prevval and in cur.val cur.next.val for a local maximum, or cur.val prevval and in cur.val cur.next.val for a local minimum. If we find a critical point and it's the first one, we update first critical point to the current index. Otherwise, we calculate the distance from the current critical point to the previous one and update min distance if this new distance is smaller. At this point, if a critical point is found and it's not the first one, we also calculate the maximum distance by subtracting the position of the first critical point from the current index. This ensures that max distance is always updated to reflect the furthest spread between the first and current critical points identified so far. To keep tracking subsequent critical points, we update prev critical point to the current index before moving forward in the list. After processing the current node, we advance our pointers by setting previous to cur to cur.next, and incrementing the index. This loop continues until we traverse the entire list. Once we exit the loop, we check if there were fewer than 2 critical points by verifying if min distance is still equal to integer.max_value. If that's the case, it means we couldn't calculate any valid distances, so we return -1, -1 as specified in the problem. Otherwise, we return an array containing both min distance and max distance, which represent the smallest and largest distances between any 2 critical points in the linked list. Finally, we define the list node class, which represents the structure of a singly linked list node. Each node contains an integer value, val, and a reference to the next node, next. The class provides 3 constructors, a default constructor, one that initializes val alone, and another that sets both val and next. This definition ensures that our solution can interact seamlessly with the input list provided in the problem. With this implementation, the algorithm efficiently identifies and processes critical points in the linked list to compute the required distances while maintaining a clear and logical structure. The use of simple variables and a single traversal helps achieve an optimal solution with minimal overhead. To solve this problem, we start by initializing the key variables and pointers. Variables include first_cp and prev_cp for tracking the first and previous critical points, respectively. We also set min_dist to infinity and max_dist to -1, which will store the minimum and maximum distances between critical points. For traversal, we initialize previous as none, cur pointing to the head of the linked list, and cur_index to 0. At node 1, since previous is none, we cannot perform a critical point check, so we simply move the pointers forward. Now previous points to node 1, cur moves to node 2, and the index is updated to 1. At node 2, we check if it's a critical point by evaluating if the value of the current node is greater than its neighbors. Since 132, node 2 is a critical point. We record this as the first critical point by setting first_cp and prev_cp to 1. The pointers are then updated, with previous moving to node 2, cur moving to node 3, and the index increment to 2. At node 3, we again check if it's a critical point by evaluating its value relative to its neighbors. The condition 325 is true, so node 3 is identified as a critical point. Since this is the second critical point, we calculate the distance between it and the previous critical point. The distance is 2, 1 equals 1, so we update min_dist to 1. Similarly, max_dist is updated to 1 at this step, and prev_cp is updated to 2. The pointers are then moved, with previous now pointing to node 3, cur to node 4, and the index updated to 3. At node 4, we check the critical point condition again. The inequalities 251 hold true, so node 4 is another critical point. We recalculate the distances. The new minimum distance remains min 1, 3 to 2 equals 1, while the maximum distance is updated to 3, 1 equals 2. We then update prev_cp to 3 and move the pointers forward, with previous now at node 4, cur at node 5, and the index at 4. Finally, at node 5, since there is no next node, the critical point check cannot be performed, so we end the traversal. After completing the traversal, we analyze the results. The minimum distance between any two critical points is stored in min_dist, which is 1, and the maximum distance between them is stored in max_dist, which is 2. Therefore, the result for this example is 1, 2. In the second example, we start by initializing the same variables and pointers as before. Here, the linked list values are 5, 3, 1. At node 1, we cannot perform a critical point check because there is no previous node, so we move the pointers forward. At node 2, the critical point condition 531 is evaluated, but it is false since the values do not satisfy the inequality. The pointers are then moved forward to node 3, but since there is no next node at this point, we cannot perform the check, and the traversal ends. Following the traversal of the second example, we find that no critical points were identified. In this case, both first_cp and prev_cp remain none, indicating that there are no critical points in the linked list. As a result, we return -1, -1, which signifies that no critical points exist. In the third example, the linked list contains the values 1, 2, 3, 4, 5. We initialize the variables and pointers as before. Here, we will traverse through the nodes and evaluate the critical point condition for each. During the traversal of the third example, we check the critical point condition for each node. At node 2, the condition 1, 2, 3 is evaluated and found to be false. Similarly, at node 3, the condition 2, 3, 4 is false, and at node 4, the condition 3, 4, 5 is also false. Since no nodes satisfy the critical point condition throughout the traversal, no critical points are identified. Consequently, the result for this example is also -1, -1, indicating the absence of critical points in the linked list. The time complexity of this solution is O(n), where n represents the number of nodes in the linked list. This is because we perform a single traversal of the entire list to identify critical points and calculate the minimum and maximum distances between them. Let's break this down step by step. First, we initialize several variables such as first_cp, prev_cp, min_dist, max_dist, and pointers like previous, cur, and cur_index. These initializations are done in constant time, or O(1). Next, in the main traversal of the linked list, the while loop processes each node exactly once. For each node, we check whether it qualifies as a critical point by comparing its value to its neighbors. This operation is constant time, O(1). If a critical point is found, we update the min_dist, max_dist, and prev_cp variables, all in constant time as well. Finally, we move the pointers and increment the index, which are again constant time operations. Since each of these steps is proportional to the number of nodes, the overall complexity of the traversal is O(n). After the traversal, the algorithm performs one final check. If there are fewer than two critical points, it directly returns -1, -1 in constant time, O(1). Combining all of this, the dominant cost is the traversal itself, leading to an overall time complexity of O(n). The traversal of the linked list is the dominant factor, so the overall time complexity remains O(n). Now, let's discuss the space complexity. This solution achieves a space complexity of O(1), meaning it uses a fixed amount of extra memory that does not scale with the size of the input linked list. Breaking this down, the algorithm uses a constant number of variables, such as first_cp, prev_cp, min_dist, max_dist, previous, cur, and cur_index. Each of these variables occupies a fixed amount of space, which is O(1). Importantly, the algorithm does not create any additional data structures or make copies of the input linked list. It operates directly on the input provided, without allocating space proportional to the size of the list. Therefore, the memory usage remains constant, regardless of the number of nodes in the list, resulting in a space complexity of O(1). Let's examine the best, average, and worst-case scenarios for this solution. In the best case, the linked list contains fewer than 2 critical points. Even in this scenario, the algorithm must traverse the entire list, so the time complexity remains O(n). However, no updates are made to the min_dist or max_dist variables. In the average case, the list contains a few critical points. The traversal still takes O(n), and updates to min_dist and max_dist occur in constant time for each critical point. In the worst case, the linked list contains a large number of critical points. Even with frequent updates to min_dist and max_dist, these updates are performed in constant time, and the overall traversal still takes O(n). To compare, a brute force approach might involve iterating through every pair of nodes in the list to identify critical points and calculate distances. This naive method would require a nested loop, leading to a time complexity of O(n²). For each node, the algorithm would traverse the remaining nodes to calculate distances, resulting in quadratic growth in runtime. The current solution avoids this inefficiency by using a single traversal. The optimized solution significantly improves upon the naive approach in 2 major ways. First, it uses a single traversal of the linked list, reducing the time complexity from O(n² to O(n). Second, it avoids creating additional data structures, which keeps the space complexity at O(1). Let's confirm this mathematically. If n represents the number of nodes, the while loop runs exactly n iterations. Each iteration performs a constant amount of work, such as comparisons, updates, and pointer movements. This makes the total cost proportional to n, resulting in a time complexity of O(n). Additionally, since no extra memory is allocated beyond the fixed set of variables, the space complexity remains O(1). Overall, this optimized solution is highly efficient, achieving linear time complexity and constant space complexity, which makes it well-suited for handling large linked lists. When tackling this problem, there are several common mistakes to be aware of. First, ignoring edge cases can lead to runtime errors or incorrect results. For example, a list with fewer than 3 nodes cannot have any critical points because a critical point requires both a previous and a next node. Similarly, if all nodes in the list have identical values, there will be no peaks or valleys to identify. Another frequent mistake is misunderstanding the definition of a critical point. Strict inequalities must be used to determine if a node is a peak or a valley, meaning the value at the node must be strictly greater than or strictly less than its neighbors. Confusing this with non-strict inequalities can result in false positives. Finally, many candidates fail to optimize for large inputs. While a brute force approach might work for small lists, it becomes inefficient for larger ones, such as those with up to 100,000 nodes, often leading to time limit exceeded errors. Efficient algorithms are crucial for competitive programming scenarios. Another common pitfall is unnecessary space usage. Some solutions store all nodes or intermediate results, which increases space complexity. Instead, you can process the list in a single pass while only maintaining the essential information, like the indices of critical points. This keeps the memory usage minimal. Off-by-one errors are also common, particularly when indexing nodes are switching between 0-based and 1-based indexing. These mistakes can lead to incorrect distance calculations or even index out-of-bounds errors. Paying close attention to how indices are handled in the list will help avoid these issues. Overall, ensuring your solution is both space-efficient and error-free in terms of indexing is key to solving this problem effectively. Now, let's discuss some insights for interviews. This problem is designed to test your ability to recognize patterns, specifically identifying peaks and valleys in a sequence. Efficient traversal while maintaining the context of previous and next nodes is a critical skill here. Handling edge cases is another area interviewers may focus on, such as ensuring your solution works for lists with no critical points or multiple consecutive peaks and valleys. Additionally, you should be prepared to discuss optimizations. For example, transitioning from an O(n)² brute force approach to an O(n) single-pass solution demonstrates an understanding of trade-offs between time and space complexity. Follow-up questions are also common. You might be asked to modify the problem, such as counting the total number of critical points, manipulating the list in place, or solving the problem recursively instead of iteratively. Lastly, related problems like finding a single peak element, checking if a linked list is a palindrome, or using two-pointer techniques are worth reviewing, as they often share similar traversal and manipulation concepts. Finally, let's consider alternative approaches to solving this problem. The brute force method has a time complexity of O(n)². This involves iterating through the list twice to check every node. While it's simple to implement, it's not practical for large inputs due to its inefficiency. A more efficient approach is the single-pass solution, which works in O(n) time. By traversing the list once and maintaining references to the previous and next nodes, you can track critical points and calculate distances on the fly. This method requires careful bookkeeping but is highly scalable. Another approach is to use recursion to identify critical points and compute distances. While this can be an elegant solution, particularly in functional programming contexts, it comes with the trade-off of potential stack overflow issues, especially for very deep recursion in large lists. Choosing the right approach depends on the problem constraints and your familiarity with these techniques. Great job! We've covered the problem, analyzed the approaches, and highlighted key insights. Remember to practice and apply these concepts to similar problems. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!